Recording here. All right, welcome. It is week number 14, Algebra 2. We are starting something new this week. We're going to start our journey, our long journey of probability, which really isn't too long because it's only 3 weeks. 3 weeks of probability and we're done. Now, this week probably is the hardest part, learning how to do the counting principle. Next week, we're going to be doing independent and dependent events. Super, super easy. This week, there will be a couple problems that might throw a loop at you, but I don't think too many of you will have will struggle with it. But next week, it gets much easier. This week, what we're going to do is we're going to be talking about the fundamental counting principle. And when you do probability, so I really shouldn't even talk about probability this week. What we're dealing with this week is the fundamental counting principle. And that's just because when you're doing probability, you have to know how big the sample space is. And if you don't know how to figure out the sample space, you can't do probability. So this week we're going to be talking about the fundamental counting principle. And if you read this, the fundamental counting principle, it says let E1 and E2 be two events. The first event, E1, can occur in M1 different ways, and E1 has occurred, E2 can occur in M2 different ways. The number of ways the two events can occur is M1 times M2. What the heck does that mean? I mean, I wish math books would write stuff in English, not in mathematics, because it's so hard to understand what they're talking about. So here is what they mean. Here's an example. It says, at a high school cafeteria, diners can choose one vegetable from a choice of 5 vegetables, one meat from a choice of 2 meats, one serving of bread from among 2 breads, and a dessert from among the 3 desserts. How many meal configurations are possible? Now, I know some of you probably have done probability before, and you probably made out these. We used to, when I was doing probability in the olden days, we used to make these. I'm not even sure what they're called. They're like T-charts of sample space. And what you do is you would say, okay, I have 5 choices of vegetables. So you'd make this chart out: 1, 2, 3, 4, 5. And I don't know what the vegetables would be. You could have carrots and corn. Probably wouldn't be too easy to start with the same letter. You could have broccoli and cauliflower. We don't want to go with cauliflower. Zucchini and one more vegetable here. Peppers. Okay. My wife is giving me some hints here. So I have 5 vegetables, and then it says one meat from a choice of 2 meats. Well, okay, so from this corn, we could have beef or chicken. From this carrots, we could have beef or chicken. From this broccoli, we could have beef or chicken. And you can see how, and then from here, you could do 2 breads, and then you would count all of these things up. Takes a long time, especially if there's a lot of different events in there. So we don't usually do that. We use what's called the fundamental counting principle. Fundamental counting principle says that the total number of ways these can occur is all you have to do is multiply each one. So I have a choice of 5 vegetables. Okay, so I've got 5 times one meat from a choice of 2. So I have 2 choices of meat, 2 choices of bread, and 3 desserts. So now, if I just multiply that up, 5 times 2 is 10, times 2 is 20, times 3 is 60. I have 60 choices, and we could make it out. We could do that. You could have broccoli, chicken. I don't know what kind of bread we have. Rye bread, and a dessert of ice cream. All right. Or you could have chicken and carrots. And so there are 60 different ways you can make that up. Do you want to make that whole sample space out of 60 things? And I hope the answer is no. You don't want to make that sample space up. So that's why we use the fundamental counting principle. So we can figure out how many choices there are. Because when we do probability, it will ask you, what is the probability that you choose, broccoli, corn, broccoli, chicken, rye bread, and ice cream? And in order to do a probability, we need the sample space. Well, the sample space would be here 60. And you're right, it would be 1 out of 60, right? So that's what we're leading to. We're trying to get to the point where we can find probabilities, but in order to find a probability, we need to learn how to do the counting principle, okay? So the counting principle just means you just multiply them all together. Now this one, a little bit trickier. It says a company, C. Esta, I love that name, has 10 members on its board of directors. In how many different ways can it elect a president, a vice president, a secretary, and a treasurer? Okay, so, and this is problem number 3 on the assessment this week. Okay, see how it says problem number 3? So hopefully nobody gets this one wrong. Now, Angela, you're going a little bit too far ahead of us. You're giving an answer before we even know what that formula stands for. But if you think about it, you can use a counting principle on here. We want to, there's 4 different places, right? President, vice president, secretary, and treasurer. Okay, so there's 4 choices. How many choices do we have for the first person? And when you think about it, 10. How many choices do we have for the second person? Now, remember, we already chose somebody for this spot right here. 9. How many choices? 8 times 7. So this really is the fundamental counting principle. 10 times 9 times 8 times 7. What does that equal? So we don't get this problem wrong on our assessment. Is that 5,040? My 720? Is it 720? 5,040? How can we be so off? How can one person have 720 and one person have 5,040? Angela, did you multiply this out wrong? All right, so I'm going to go with 5,040, I believe, is the correct answer. Okay. So when you get to this problem on your assessment this week, hopefully you have 5,040 for an answer. All right, so that basically is a counting principle. Now, they do get into permutations and combinations. Okay, what is a permutation? What is a combination? You're going to need to know that when we start doing probability. A permutation is when order matters. Like in this problem that we just did, this would be a permutation because you have a president, a vice president, so on and so forth. And we'll talk about when order matters and when it doesn't matter. And there is a formula for this. This formula is called the permutation formula and is n factorial over n minus r factorial. What's a factorial? This is a factorial. If I asked you, if I said, what is 4 factorial? You would say, okay, that's 4 times 3 times 2 times 1, which is 4 times 3, which is 12 times 2, that's 24. Okay, that's what a factorial means in math. Now, in the last problem, this order mattered, right? Because it was president, vice president, and so forth. So order matters. So in the last problem, we would have written it out as 10 permutate 4. Okay, 10 permutate 4. So if I was going to use this formula, n, this is the biggest number is always n, r is the small number. So this would be 10 factorial over 10 minus 4. Well, 10 minus 4 is 6 factorial. Now, when you have a problem like this, let me show you how you would work this out. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. These all cross out, don't they? So you're only left with 10 times 9 times 8 times 7, which is what we ended up with an answer of 5,040. Now, there's another way to do it. It's called Desmos. Desmos has this function on it. Okay, so let me show you how to use Desmos, because a lot of your problems tonight, I mean, should you be able to do it by hand? Yes. But then you should be able to also use a calculator to do it. So let me show you how to use a calculator to do this problem. Okay, so I'm going to share an application screen here with you guys. Okay, I want to share Desmos. All right. So you guys should be able to see my Desmos screen here. Okay. If it's a graphics calculator, it will have it on there. Angela, is yours a graphics? If it's a graphics calculator, we'll have it in there. It's just, you just have to find it. And a lot of times it's under probability. What type of graphics do you have? Yeah, Casio, I can't help you on that one. I think your sister has a TI-84, doesn't she? Steal hers. I think it's on there. All right, so if we're on Desmos, what we're going to do is we're going to hit this little keyboard down at the bottom. Then we're going to hit functions, and we're going to scroll all the way down to where it says NCR or NPR. Now, before we do that, you always have to put the first number in. So this one was 10 permutate 4, right? So you have to put 10 here. You have to put the first number in, hit NPR, and then we put the last number in, which was 4, right? Hit enter. Oh no. Did I forget how to do Casio? All right. I know how to do it on my calculator. Maybe it's not the same. Oh, never mind. I think I do remember that you don't put this number in. You put it in the parentheses. So you put 10. I think you put 10 comma 4 in. There you go. All right. So when you use a calculator, you have to put the 10 in first and then you hit the button. But when you're using Desmos, you just inside the parentheses, you just put the N comma R in there. Okay. Does that make sense? Oh, thank goodness I had to think on the fly there. Okay, so Desmos will do your problems for you guys tonight. So when you're dealing with these types of problems, just go to Desmos. Now, as I said, you should be able to do them without Desmos. You should be able to mathematically solve them, but you know why. All right, so let's see here. So I need to go back to my screen here. All right, so that was permutations. And permutations, order matters, okay? You got to remember that. So now the next problem, number 1, it says evaluate each. So this is a problem on our assessment this week, okay? Now I'm going to do it by hand. I want you guys to do it using Desmos, okay? So this would be 8 factorial over 8 minus 3 factorial, so that's 5 factorial. So that would be 8 times 7 times 6, because the 5, 4, 3, 2, 1 would cross off. So my answer would be 8 times 7 times 6. My answer would be 336. All right, am I right? Did Mr. Shanklin beat Desmos? I probably didn't beat Desmos, but I mean, you can do it that way, okay? Because remember, the formula is n factorial over n minus r factorial. So the n was 8, so this was 8, and then 8 minus 3 is 5. And then all I did was I looked at this and I said, okay, it's just 8 times 7 times 6. Oh, you guys are faster. Oh, all right, so 336 should be the answer. That's permutations. All right. Then we have to talk about combinations. Combinations is when order doesn't matter. Now, order doesn't matter. What does that mean? Okay. Here's my best example for order doesn't matter. Okay. I love pizza. All right. So let's say I go into Pizza Hut. All right. I go into Pizza Hut and I'm going to order a pizza. I go up to the counter. I say, I want ham, pineapple, and bacon. One of my favorites. Okay. And they take my order. They go in. They start making. They're making my pizza. And then I go back like 5 minutes later and I said, no, that's not the pizza I want. I don't want ham, pineapple, bacon. I want bacon, ham, pineapple. Okay? Is that the same pizza? Somebody watched the video. That's the exact same pizza. So that's what it means when order doesn't matter. It doesn't matter if I order ham, pineapple, bacon, or if I order bacon, ham, and pineapple. Makes no difference at all. You're going to get the same pizza. So that's what it means when they say order doesn't matter. That's a good example of order doesn't matter there. Okay? Now, the formula for this is, if you think about it, isn't it the exact same formula as we had for permutation right here? This is the permutation formula. And then they're dividing by r factorial again. And you know why? Because that takes care of all of the repeats. All of those would be gone. So that's exactly too many. Now, does Desmos do combinations? Absolutely. So remember, all you have to do is use Desmos on these types of problems, but you should be able to do it without Desmos. So when you're doing a word problem tonight, it says when solving problems, and all of the problems tonight are going to be like that. They're going to be like word problems. You got to read it through and you got to decide, is it a combination or is it a permutation? When solving problems involving counting principle, you need to be able to distinguish among the various counting principles in order to determine which is necessary to solve. Number one, is order important? If order is important, you use permutation. If order is not important, use combination. And you can also use the fundamental counting principle. So in this problem right here, it says 9 weightlifters are competing in the deadlift competition. In how many ways can the weightlifters finish first, second, or third? Does order matter in this problem? Yeah, because it makes a difference if you're first or third. So in this problem, if I had to write this problem down, I would write down 9 permutate 3. So if I was going to do it by hand, see if you guys can beat me down with it, that would be 9 factorial over 6 factorial, which would be 9 times 8 times 7. 9 times 8 times 7, 9 times 8 times 7, I get 504. So did you guys beat me using Desmos? And you probably did. Just, you should be able to do it without Desmos, okay? I'm just saying that you should be able to, but I'm not saying you have to use Desmos or you have to use the formula. You can just use Desmos tonight. All right, so our practice for this week. Let me see if I have the right Desmos presentation up there. All right, let's take a look at that. In problem number 1, now, as I said, most of your problems this week are going to be word problems. So in problem number 1, it says, in how many ways 2 students can be chosen from a class of 20 students? Okay, 2 students in a class of 20 students. Does order matter or does order not matter? Order does not matter, right? Because if you, and how do I do this when I think about order mattering? Oh, no, I did not share this, did I? I'm sorry. I did not share this. I apologize. You can't see what I'm working on. Okay, so this is right. Okay, so now you guys should be able to see my screen here. Okay, so when I do order matters and order doesn't matter, all I do is I go like this. I'll say, okay, I've got Bill and Jill. I've got 2 students. 2 students can be chosen from a class of 20. Is that the same thing as choosing Jill and Bill? Would that be the same choice? And it is. These are the, if I chose 2 students and I chose these 2, it doesn't matter which order I have them. It's the same 2 students. So order doesn't matter here. So in this problem, I would do 20, choose 2. And then I would go to Desmos and I'd get my answer. All right. And what is our answer for this problem if we did 20, choose 2? And I could, again, I could do it without using Desmos. I mean, I'd go 20 and then 20 factorial over 18 factorial times 2 factorial. That would be, so this would be 20 times 19 divided by 2 factorial, which is just 2. So 10 times 19, 180. Woohoo! So I can do it pretty quickly without having used Desmos, but the answer is A, or 190. What function is it in Desmos? NPR. No, well, this one was NCR for that one. All right, so fairly easy. It's not difficult. Okay, problem number 2. It says a high school, oh, I think we did this one already. It says at a high school cafeteria, diners can choose 1 vegetable from a choice of 5 vegetables, 1 meat from a choice of 2 meats, and 1 serving of bread from among 2 breads, and a dessert from 3 desserts. So we already did this one. We came up with 60, but if I had to do it again, This would just be the fundamental counting principle. So I've got 5 choices of vegetables, 2 choices of meat, 2 choices of bread, and 3 choices of dessert. This is just fundamental counting principle. Just multiply across. And I believe we came up with 60 for an answer there. All right, so fairly easy problem. Problem number 3. Number 3, it says, how many 3-digit numbers can be formed if the leading and the ending digits cannot be 0? Oh boy. In this problem, I'm using the fundamental counting principle right off the bat. So in this problem, if I was looking at this, it's like, okay, a 3-digit number, 1, 2, 3. How many choices do I have for the first digit? Okay, how many choices do you have for the first digit? If you cannot use 9, or I'm sorry, 0. So you have 9 choices. You could have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 choices. How many choices do I have for the second digit of this problem? 10. That's exactly right. The middle digit could be 10. How many choices do I have for the last digit? And they said the last digit cannot be 0. So I have 9 choices. 9 times 10 times 9, what is that? 810 different 3-digit numbers I could have if the first and last digit is not 0. Now, could you write them all down? Could you make a sample space for all 3-digit numbers? Sure, you could. I mean, you could start off, if some teacher asked me to do this, 101, 102, 103, 104, 105, blah, 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 810 of them you're going to have to come up with. That is called a sample space. Not really excited about making a sample space if I had to of 810 different objects, but I could. Just don't want to do it. And I would never ask you guys to make a sample space like that. All right. Problem number 4. Problem number 4, it says 3 gentlemen and 3 ladies are candidates for 2 vacancies. A voter has to vote for 2 candidates. In how many ways can one cast his vote? Okay. So how would I do this one? Now, does it make any difference that they were gentlemen and ladies in this problem? No, because you're just voting for 2 people out of a total of what, 6? And order doesn't matter, does it? So in this problem, if order doesn't matter, I'm looking at this and I have 6 choices, 6 choose 2. So if I'm going to do this, again, I'll do it the long way, just to show you that it can be done. Okay, this is my n value, this is my r value. So it's going to be 6 factorial over 6 minus 2, which is 4 factorial, times 2 factorial. Well, I always take the biggest numbers on top and bottom. So 6 factorial and 4 factorial just breaks down to 6 times 4, doesn't it? Because the rest of them would cross off. And then I still have 2 factorial on the bottom, which is just 2. So 6 times 4 divided by 2. Uh-oh, something went wrong here. Did I mess this up? Oh, that's 6 times 5. Ugh, I don't even know. So 6 times 5, and then the 4, 3, 2, 1 cross out. So, all right. So 15. Whoa, I don't even know how to count backwards anymore. Thank goodness I'm retiring. I can't count backwards from 6. Wow. All right. So my answer should be 15. It doesn't. If it's Samantha, if it's permutation, if order matters, then you can do it just by multiplying all the possibilities together. If it's order doesn't matter, you can't do that. Then it's not. You can't. if order matters, or if order doesn't matter, you really can't do the blank, 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 the fundamental counting principle, because you're not dividing all the repeats out. So that's usually when it's permutation, you can just do the lines. If it's if it's combination, you can't, because combinations, you've got all that overlap that has to be divided out. Now, if you remember to divide that out, you can do it that way, but most kids don't. Most kids don't remember that. Yeah, you could have, order doesn't matter. So you'd have to divide out that 2, the overlaps. That's why in this problem, order didn't matter, right? Now I got to go back. I forgot what we were doing here. Yeah, so order did not matter in this problem, because it doesn't matter, you know, if you elected Jim and Bob, or Bob and Jim, they're both elected. It didn't matter which order you had them. So if you did it, you could have done it 6 times 5 divided by 2, because that would be your overlaps. Anything, there'd be the 2 overlaps. So that way, that one wouldn't have worked. So combinations, when you're doing combinations, when order doesn't matter, you don't want to just draw your lines out. That usually messes things up big time. Yeah, order matters, order doesn't matter. That's a biggie. And that's where most kids struggle with this, is deciding if order matters or order doesn't matter. That is the hard one, the hard part. All right, number 5. It's easy problem. Evaluate 8 permutate 3. So I could use n factorial over n minus r factorial, which gives me 8 factorial over 8 minus 3. That's 5 factorial. So that's 8 times 7 times 6, which is, I don't know, I didn't multiply it out. So 336 is the correct answer. All right. Now, problem number 1 on the assessment just has, I think, 4 of these types of problems, where I just ask you what the permutate or combination is. And you can do it with Desmos. You don't have to work it out. Okay. Oh, there's, when I make out my thing, I always put prompts in. Okay, evaluate using a graphing utility. What is 15 permutate 6? Okay, 15 permutate 6. And I'm not going to do this one because it would take me a little bit of time to multiply it out. So it comes out to be 3,603,600. Thank goodness for calculators, right? Thank goodness for Desmos. Okay, so letter B is the correct answer for that one. All right. Number 7. Oh, I'm going to tell you that a lot of you are going to mess this problem up. I messed it up when I first started it. It says, how many permutations of the letter of the word apple are there? And I did get the wrong answer when I did this one real quickly. Okay. 4 letters of each slot. So when I did this problem, I looked at it and I said, oh, permutations. It's telling me permutation. And I looked at it and said, okay, so I have how many permutations of the letter of the word apple are there? So I've got 1, 2, 3, 4, 5. So there's 5. But really, isn't there only 4 choices? Because you have 2 P's in there in that problem. It repeats, yeah. So what is my answer? Just letter D? Is that right? And if you worked it out, I think it just becomes 5 factorial over 5 minus 4, which is 1 factorial, which is 5 factorial, which is 5 times 4 times 3 times 2 times 1, 20, 60, 120. Okay. Okay, so that is incorrect, isn't it? So let me jump in here, see what my practice says. Let's see here. So this is week number 14. Practice. All right. What number was this? Number 7? No, number 7. I did have D there. So I'm going to get rid of that and put B. All right. Yeah, it should be 120. Yep. All right. Let's see here. Number 8, or problem number 8. Oh, that is really small. Number 8, it says, oh, I think we did this one already too, didn't we? 9 weightlifters are competing in a deadlift competition, and how many ways can the weightlifters finish first, second, and third? So in this problem, order does matter. Okay, it makes a big difference if you're first, second, or third. So if I was going to do this problem, I'm going to do permutate. I've got 9 weightlifters, permutate 3. Okay, and we did this one already, and we came up with letter A, 504. So permutations, combinations. And you know, this whole new chapter deals with probability. Next week we will be doing a lot of probability, but being able to find the sample space really does help. Okay, so doing this week will help us next week. All right, problem number 9, I believe. There are 13 patients in Dr. Ziegler's waiting room. Dr. Ziegler can see 5 patients before lunch. In how many different orders can Dr. Ziegler see those patients? Okay, so it says in how many different orders. So order matters in this problem, doesn't it? Because he says specifically in how many different orders could he see. So Bill and Jill is different than Jill and Bill because that is a different order. So in this problem, I would use a permutation. I would say, okay, I've got how many patients? I've got 13 patients, permutate 5. Now, this is somebody was asking about, can I do the lines here? Sure, in this problem you could. So how many ways could he see the first patient? 13. How many ways could he see the second patient? Well, he's already seen 1 patient, so that would be 12, 11, 10, 9. So you could just multiply that out. You could just go 13 times 12 times 11 times 10 times 9, right? So that would work also if you wanted to. Makes no difference which way you do it. Okay, does that make sense? That you could, I mean, there's a couple ways you could do these types of problems. I mean, I'm not, now, as I said, if order doesn't matter, then I wouldn't use this method because then it's like, okay, you know, then you got to divide out all the overlaps. Which, how do you know what the way they are? So that's where I would use combinations. All right. Number 10, it says, in how many ways 4 boys and 3 girls can be seated in a row so that they are alternating? Oh, this one took me a little bit of time to get to. Letter C. Letter A. I went with A. And this is what I did in this problem. I just looked at this and I said, okay, boy, girl, girl, boy. So I could have boy, girl, boy, girl, boy, girl, boy, or I could have girl, boy, and these would all be different things here. I just looked at it and said, okay, how many boys do I have? I did 4 factorial times 3 factorial when I did this problem, because it was like, okay, it doesn't really matter. I mean, I just need to know how many there are of these. So I did 4 factorial, which was 4 times 3 times 2 times 1, 24 times 3 factorial, which is just 6. So I ended up with 24 times 6, 24, 12. What is that, 144? So I ended up with 144 different ways. And that was kind of a bad problem, because it really didn't, it's kind of hard to see how the girl, boy, boy, girl is going to change around there, but it really doesn't make much of a difference there. It's just how many boys there were, how many girls, and that would make the difference there. So the answer should be A, 144. Well, but you're talking about, so you're talking, so here, look, you've got Jim, Bill, Zach, and I don't know, Sean. And then for girls, you have, I don't know, I just want to use different letters because I don't want to. So you could have, and this is where it gets interesting, because you could have, let's go Mary, and I don't want to put Jane in there because that'd be a Jane again. Okay, so you could have J, L, B, M, Z, A, S, and then you could just switch one of these, and that would be another combination. It could be B, L, J, M, Z, A, S. There's a lot of ways that they can be switched around. That's why it's just a number of boys and a number of girls. Yeah, that one, that after I looked at it, it's like I shouldn't have put that one on there. It is out there. Yes, but they're asking if they were specific boys and specific girls, switching them up. How many different ways could you switch them up? Well, there's 4 boys and 3 girls. 4 different boys, so I did 4 factorial, and 3 different girls. So I just used the fundamental counting principle of, how many ways. So I just used the fundamental counting principle. 1, 2, 3, 4, 5, 6, 7. How many ways can a boy sit here? 4. How many ways can a boy sit here? 3. How many ways can a boy sit here? 2. How many ways can a boy sit here? 1. There's only 4 boys, and there's 3 girls. How many ways can a girl sit here? 3. How many ways can a girl sit here? 2. How many ways can a girl sit here? 1. Well, that is 4 times 3 times 2 times 1. That's the boys. So that's 4 factorial. And then the girls, 3 times 2 times 1. That was my thinking process when I was doing this problem. It's like, okay, I'm just gonna, how many ways can I put a boy here? And I just put them one in between each other. So that was my thinking when I did it. I know it's not. That was a kind of a problem that was out there. I will say that it's a little bit out there. I wouldn't put anything like that on the test. Yes, exactly. Yes, the same thing. Right, Samantha. Did you do the lines then? And I just represented it as 4 factorial and 3 factorial instead of, yeah, okay, awesome. Very good. That's exactly the way I was thinking. I should have just put the lines down in the beginning. It probably would have made more sense. Sorry about that. All right. That's it for this week. I will tell you next week, you guys are going to really enjoy it. We start with probability. It's probably one of the easiest weeks we've had. And so the last 2 weeks are going to be really super easy. Oh, did I not? Oh, I didn't submit it yet. I'm sorry. It should be B now. I didn't submit. Sorry. All right, you guys have a great week. Saturday and Sunday are supposed to be beautiful outside. Get outside and enjoy the weather. I know it's a couple days away, but we're next week on Monday. I think it's supposed to be 72 degrees. I will be outside teaching class next week at this time. Guaranteed. You guys have a good one. Bye.